Welcome to an interactive course designed to validate and improve our knowledge of heat treatment. The topic of this course is carburizing under reduced pressure. The first attempts to develop a low-pressure carburizing process can be dated back to the 1960s, and efforts to introduce it industrially can be seen in the following decade. Although no longer relevant today, it is interesting that the impetus was a 1977 Russian patent for the production of acetylene. This subsequently led to the filing of a U.S. patent for acetylene-based carburizing, but it was not low-pressure carburizing. The first patent for LPC with acetylene dates back to 1996 and is registered in the name of IHI Machinery and Furnace Corporation under number US 5702540A. However, it was also a spontaneous development with the support of major vacuum furnaces manufacturers such as ECM Technologies from Grenoble in France, ALD Vacuum Technologies from Hanau in Germany, or Seco Warwick from Polish Świebodzin. However, there are many more systems with LPC on the market, and practically all vacuum furnaces manufacturers have already included this process in their portfolio. An example is the Italian TAV vacuum furnaces, the French Fours BMY, or the Chinese manufacturers SAMT or Fulcrum. The choice is huge. Currently, low-pressure carburizing is so widespread that it can be considered a standard process. It is used in various industries, but especially in the automotive. However, there are only two major players left in this industry, which represent the technological leader in terms of quality. These are the French ECM and the German ALD. The concept of their equipment will be explained later. But what is the goal of this technology? To understand this better, we need to go back to the iron cementite diagram. Carburizing is the process of saturating a surface with carbon at temperatures corresponding to austenite. In case of carburizing, it is used that sub-eutectoid steels with a low carbon content 0.1 to 0.2% and a high portion of ferrite are soft and tough after quenching. However, if the surface of the steel is saturated to a certain depth with carbon, usually to a concentration of eutectoid point of 0.8%, then this surface after quenching is very hard of up to 65 Rockwell. Thus, we get a tough core with relatively high strength and high toughness, and at the same time a very hard and abrasion-resistant surface. The principle is therefore the same as in conventional carburizing, only the process of obtaining carbon takes place under reduced pressure. To ensure the carburizing process, the parts must be heated to the austenitizing temperature, and a carbon source is needed. Since case-hardening steel has a very low content of this element, the carburizing temperature, according to the iron-iron carbide diagram, will be high, above the A3 temperature, usually between 900 and 1000 degrees Celsius. The carbon source can be various media, gaseous or liquid, but in the case of low-pressure carburizing, it is always a gas. The saturated gases can be different. It can be acetylene, propane, methane, ethylene, or it can also be a combination of them. For example, Seco Warwick also uses a mixture of acetylene, ethylene, and hydrogen. However, we must take into account that acetylene is a catalytically decomposable hydrocarbon, which essentially means that it catalytically decomposes into its elemental components when it comes into contact with the iron surface. Other hydrocarbons, such as methane and propane, are thermally decomposable, meaning they decompose immediately upon entering the hot zone of a vacuum furnace, eliminating the ability of carbon to react with the steel surface to form undesirable hydrocarbon byproducts and ultimately contaminate the hot zone. Acetylene also has a higher average carbon flux, approximately 150 grams per square meter and per hour, than other hydrocarbons. For these technical reasons, Acetylene is a strong candidate for the preferred hydrocarbon gas of choice. The basis of this process is a vacuum furnace, essentially the same design as conventional vacuum furnaces. The only difference is that between the cold wall of the vessel and the heating chamber, there is a system of tubes designed to distribute the saturating gas evenly in the space of the heating chamber. The gas itself is then fed into the working chamber through a system of nozzles. These can be ceramic or made of quartz glass. In the case of single-chamber furnaces with LPC and quenching in a gas stream, the process begins with the chamber being evacuated to a limit vacuum and gradually heated to the carburizing temperature. However, since the majority of furnaces for LPC are furnaces with 2 or more chambers, the carburizing chamber is permanently under vacuum and permanently at the working temperature. The batch is therefore loaded into the already heated chamber and gradually heated to the austenitizing temperature. Once it is reached, carburizing gas begins to be introduced into the furnace. If the carburizing gas acetylene comes into contact with the high temperature of the surface of metal parts, its catalytic dissociation occurs. The acetylene releases atomic carbon, which is capable of diffusion. The remaining hydrogen is sucked away by the vacuum furnace pumping system. However, once the carbon penetrates the steel surface, the next process is the same as in classical carburizing, governed only by diffusion laws. The advantage of the vacuum carburizing process is that, unlike classic carburizing, oxygen does not participate in the reactions. This is significant in that intercrystalline oxidation does not occur on the surface, measured by the IOD parameter, internal oxidation depth, according to ISO 15787. This reduces the mechanical properties. Another advantage is the fact that we can go to significantly higher carburizing temperatures and thus significantly speed up the process. Given the shorter times, there is no risk of excessively coarsening the austenitic grain. This table shows the results of an experiment by the company Icolin, investigating the time it takes for grain coarsening to occur for individual steels at a given carburizing temperature. The table shows that even at a temperature of 980 degrees Celsius, we can achieve an acceptable structure without significant grain coarsening. So even a temperature of 980 degrees Celsius for steel's 16 manganese chromium 5 or 20 manganese chromium 5 is not a major problem. We must take into account that in 8 hours at this temperature, we achieve CHD of up to 1.6 to 1.8 millimeters, and in 2 hours, then 0.6 millimeters. However, the increase in austenitic grain size can also be stabilized by other procedures, for example by pre-saturating the surface with nitrogen before the actual carburizing. In this case, iron nitrides will precipitate at the grain boundaries, which during the actual carburizing will improve the stability of the grain size even at high temperatures around 1000 degrees Celsius. This process is applied, for example, by Seco Warwick in a procedure called pre-knit, but it can also be applied on the ECM Flex and Jumbo systems. It is usual to have a separate chamber for the nitrogen saturating process and another for the carbon saturating process, but theoretically, both processes can be combined into one chamber. Acetylene decomposes by catalytic reaction with the surface of iron into carbon and hydrogen. The expected reactions are as follows. The released carbon from these reactions is absorbed on the surface and then begins to saturate the austenite. The solubility of carbon in austenite is high, up to 2.1%, but it is not unlimited. Its limitation is given by the ACM line, which represents the formation of iron carbide Fe3C cementite. The position on the ACM line is determined by the temperature of the process. The carbon from the saturated austenite travels further from the surface of the steel to the core. It travels from places where the carbon content is higher to places where there is less of it. Since the diffusion rate is dependent on the concentration gradient, in the first stage the carburizing rate is high. However, it gradually slows down as the carbon progresses deeper. In order to saturate the steel surface with carbon, we must ensure its sufficient flux. The carbon flux J is the mass increase of carbon atoms in the material and tells how many milligrams of carbon are introduced into a unit area of the batch per unit time. For example, in 1 hour of the process per 1 square centimeter of area. The formula for its calculation is as follows. In this formula, M1 is the mass of the measured sample before the process, M2 is the mass after the process, T is the sum of the times of the saturation periods, and S is the total area of the reference sample. To measure the carbon flux, we need ordinary scales with an accuracy of 1 to 100 milligrams and the ability to weigh up to 1 kilogram. The required carbon flux depends on the temperature, as well as its solubility in austenite. At the moment when the austenite is saturated due to the carbon flux, a thermodynamic equilibrium occurs between the atmosphere and the steel surface, and due to the zero gradient, the transfer of carbon to the steel slows down or stops. Acetylene that is not catalytically decomposed will not participate in the process and will be evacuated out of the carburizing cell. The figure on the left diagram shows the mass increase of carbon in the carburized layer at temperatures of 920, 950, and 980 degrees Celsius. The mass gain shows a significant decrease with a saturation period, almost stopping after 120 seconds. The middle and right diagrams show the same situation, but in terms of carbon flux. The graphs show its exponential decline. After about 120 seconds, the saturation ability of the atmosphere of acetylene stops, and the continuation of this period loses its meaning. The graphs are valid for a total pressure of 300 pascals, or 3 millibar. Therefore, in order to restore the carbon flux, the gradient between the atmosphere and the surface of the steel must be restored. The saturation period must be followed by a diffusion period, which reduces the carbon in the steel surface. There will be several of these alternating phases in the process, depending on the depth of diffusion needed. Mechanism of steel carburizing during process at reduced pressure can be described as follows. The process begins with the batch being loaded into a heating chamber, which is usually permanently at working temperature. The working procedure is therefore similar to that of multi-purpose furnaces. Because the batch is cold, it must be heated to the desired temperature throughout its full profile. This heating usually takes place in nitrogen, with convection heating up to 850 degrees Celsius, above this temperature in a vacuum. To fully heat the batch, a sufficiently long period must be applied to stabilize the temperature. Only when it can be assumed that the entire batch is at the same temperature can the carburizing begin. Proper heating of the batch is important because the carburizing gas decomposes catalytically, depending on surface temperature, in contact with the steel surface, and in order for the carburizing to take place evenly in the full cross-section, the parts must also be at the same temperature. The default amount of carbon is usually 0.1 to 0.2%, but we need 0.8%. We will achieve this by the following steps. The carburizing process begins with the first saturation period and is followed by the first diffusion period. The next periods depend on the required carburizing depth of the CHD. In our case, these are periods 4. The saturation period provides enough carbon to saturate the austenite at the ACM line. The maximum can be 2.1%, but in the case of carburizing at 960 Celsius, it will be only 1.8% of carbon. As the carbon content in steel increases with each pulse, the gradient of carbon in the diffusion profile of the layer gradually decreases. Therefore, the diffusion segments are extended in each subsequent step, so that at the end of the diffusion period, the carbon content is around 1.1%. Only the last diffusion period serves to reduce the carbon content to a eutectoid amount, to 0.8%. In order for the carbon to be evenly distributed throughout the batch, an even distribution of acetylene in the heating chamber must be ensured. This is not entirely easy, because the total pressure of up to 10 millibar during carburizing is in the area close to laminar gas flow between the inlet and outlet to the pumping system. This may mean that gas may not reach some areas at all. To minimize this effect of gas distribution in the carburizing cell, it is necessary to properly design the inlet nozzle system. In ECM furnaces, there are more than 80 of them in the heating chamber. Optimally, the flow should be turbulent, but this is difficult in low vacuum conditions, and what area we're in defines the Reynolds number. If it is lower than 2000, the flow will be laminar. Above this value, we will move to the turbulent flow, where ρ is gas density, V flow velocity, D characteristic dimension, for example nozzle diameter, and μ dynamic gas viscosity. With respect to the above formula, the Reynolds number will increase as the velocity of the gas or the diameter of the inlet nozzle increases. However, the diameter of the nozzle will determine the flow rate of the gas, and this cannot be increased indefinitely because it must be in balance with the furnace's pumping system. Another effect is the effect of the density of the gas, but it will decrease with decreasing pressure, and it will also be necessary to take into account the influence of the viscosity of the gas, which will decrease with increasing temperature. Since turbulent flow is physically difficult to achieve under the pressure and temperature conditions of low-pressure carburizing, other means must be found. For example, pulse gas injection, nozzle adjustment at different angles, or increasing injection speed or flow rate can help. In practical application, all of the above is good for understanding the low-pressure carburizing process, but the actual LPC process must be solved for us by the equipment supplier, both in terms of design, hardware, and software. Because each furnace manufacturer protects its know-how, including patent protection, this situation leads to the fact that the systems are so different that they are not compatible with each other. That is why ECM has Infracarb, Seco Warwick SimVac, Ipsen AVAC, 4BMI AllCarb, etc. The systems differ both in the design of the process data calculation and in the fact that they are either completely autonomous, such as SimVac from Seco Warwick, or are part of the furnace programming system in the case of furnaces from 4BM1 or ECM technologies. The basic problem is that some simulators require knowledge of the surface area, while others do not. If they require this parameter, we must solve it in the ERP system. So each product must have a property, which is the surface area, for example in square meters. If the batch is then being prepared, the ERP system automatically calculates all parts' surface in the process and adds the basket's surface to it. Based on this data, we then select a furnace program that determines the acetylene flow rates for a given CHD and temperature. For the SimVac simulator from Seco Warwick, it looks like this. The picture on the left shows the input data. The picture on the right shows the output data. The result can be imported into the SCADA system and therefore serves directly as a furnace program. Infracarb and ECM differ significantly from these simulation systems with calculation of carbon flow based on surface area. Whether we have a small or large surface inside the furnace, the amount of acetylene is always the same and corresponds to the maximum possible batch surface area in the device, for example of 25 square meters. We therefore do not need to know the batch surface. This has its advantages. On the one hand, there is always a sufficient amount of gas in the furnace, and it cannot happen that some parts of the charge are not carburized. On the other hand, we only have one program for all batches of the same material, for the same CHD and at the same temperature, regardless of the surface area of the parts in the batch. The question is, why this is so? This explanation is offered by Ulvac, a company that manufactures analytical instruments for gas analysis under reduced pressure and mass spectrometers. In order to carburize properly, we must maintain a catalytic reaction in the furnace according to this equation. If this is the case, we will both carburize properly and no soot will be released from the excess carbon. However, if there is an excess of acetylene and it does not decompose catalytically on the surface of the metal, but in the volume of the furnace, carbon soot is formed and settles on the components, heating elements, and walls. The cause is the excess carbon bound in ethylene. But where did the ethylene come from when we introduced acetylene? If the conditions in the hot zone change so that all the acetylene is not only catalytically decomposed on the surface of the metal of the charge, but also begins to react homogeneously in the gas volume, the acetylene molecule will react with the residual hydrogen in the atmosphere, and, according to this scheme, a portion of ethylene will be formed. This will further decompose into two CH2 molecules, and the released carbon will be deposited in the furnace. If we measure the atmosphere with a mass spectrometer, the manifestation of the pyrolytic reaction will be the growth of the ethylene peaks 14 and 28, and at the same time, the decrease of the acetylene peak 26. We must prevent this. Signs of inappropriate process settings are listed in the table. Too high partial pressure of acetylene, too long a saturation period, insufficiently heated surface of the batch and furnace, low gas flow or its distribution in the furnace, contamination of the furnace walls with carbon, or too high a proportion of oxygen in the furnace. In optimal carburizing, the acetylene content drops sharply after injection into the furnace. The amount of ethylene is close to zero, and at the same time the hydrogen content increases slightly. In risky carburizing, the accompanying phenomena are a high acetylene content, a sharp increase in ethylene, and hydrogen may also increase sharply at the same time. Based on this information, it can be stated that there will be stable areas for low-pressure carburizing and unstable areas. Stable region for LPC is in temperature range 900 to 1000 degrees Celsius and acetylene partial pressure 0.3 to 2 millibars. In this region, catalytic decomposition of acetylene takes place directly on the steel surface and no ethylene is created. Unstable region is for acetylene pressure over 5 millibars, or insufficient gas flow with spontaneous pyrolytic reaction to ethylene and with soot extraction. With low temperature below about 850 degrees Celsius, when the catalytic activity of the steel decreases and the reaction moves to the gas volume. This graph is showing more. The green region represents stable carburizing and surface decomposition of acetylene, no ethylene formation. The orange region is a zone with low temperature, pressure, and insufficient activation of acetylene, which hardly decomposes. The red area is then an area with too high pressure or poor flow, where acetylene pyrolysis to ethylene and soot formation occurs. A properly set low-pressure carburizing process has a short saturation period, a pressure of 0.5 to 2 millibars, a temperature greater than 900 degrees Celsius, and a correct gas flow without ethylene formation. For clarification, it is necessary to add that the accuracy of pressure regulation should be plus minus 0.05 mbar. As I have already indicated, there are a number of systems for implementing the LPC process. Their comparison is in this table. Practically all systems use alternating saturation and diffusion periods. However, they differ in other points. These two figures show the difference between the infracarb system from ECM and the SimVac from Seco-Warwick. In this, the ECM system is exceptional because it uses auto-regulation of the kinetic equilibrium of the carbon flux in the furnace by reaching the ACM line, with the exclusion of iron carbides Fe3C. This is also the reason why we do not need to know the area of the charge with this system. And not only that, the LPC control guarantees that we will constantly move in a stable area of carburizing without ethylene formation and without soot deposition. On the other hand, there is SimVac, which uses a thermodynamic model. It tries to simulate a situation with a defined saturation potential CP, as is the case with multipurpose furnaces. Although it works quite well in practice, the disadvantage of this system is that we need to know the surface area of the batch. This will be a problem in most heat treaters, and if we get it wrong, there may be too little or too much acetylene. However, because this calculation method does not use the maximum carbon gradient, the process will be slower than infracarb. But not only gases and their control have an effect on the formation of soot in the hot zone. Another problem is the physical contamination of the chamber with hydrocarbon vapors from the quenching oil. These two phenomena often add up and together cause the formation of sticky carbon condensates, so-called tar, soot, polymerized carbon, on the wall's heating elements and diffusers. After quenching, oil vapors are released in the quenching chamber, which get back into the heating chamber by diffusion or flow. These vapors from mineral oil polyalkylene glycols and esters have a lower decomposition temperature, 300 to 600 degrees Celsius, than acetylene. On the hot surfaces of graphite heating elements or on the surfaces of ceramics, pyrolysis of these heavy hydrocarbons occurs, and tar and soot is formed. If these layers are covered with a layer of ethylene pyrolysis, they form a conductive, insulatingly unstable coating that destroys heating elements or thermocouples. Typical manifestations are black deposits on insulation, sticky coatings on the walls of the furnace, or back contamination of quenching oil. To prevent these phenomena, we must respect certain principles when designing a furnace for LPC. We must have a high-quality vacuum-sealed door between the heating and quenching chambers, preventing contamination of the heating chamber with quenching oil. Loading system to the hot zone must be separated from the elevator, which dips the hot batch into the oil. For each batch loaded through the conveyor system contaminated with quenching oil, we can introduce oil residues into the heating chamber. Flushing the quenching chamber with nitrogen so that the transfer of oil vapors is limited before opening the vacuum seal of the heating chamber. During the actual quenching, there must be a certain nitrogen pressure above the oil level, improving both the oil cooling curve and reducing oil evaporation. Oil condensers must be installed on vacuum pumps to capture oil vapors, preventing their recirculation into the process chamber. Periodic burning of the heating chamber should be applied at a temperature above 900 degrees Celsius and a pressure of less than 10 pascals. Quenching oils with a minimum vapor tension should be used so as to prevent its evaporation. From the point of view of heating chamber maintenance, it is recommended every 100 to 150 cycles, visual inspection of the interior, measurement of heating resistance. Every 500 cycles, burn-off cleaning. Every 1,000 cycles, cleaning of the vacuum pump and gas distribution pipes. Once a year, replacement of filters and sealing elements in contact with the furnace atmosphere and replacement of nozzles. For carburizing under reduced pressure, it is also necessary to consider the type of acetylene. It can dissolve in both acetone and DMF, which is dimethylformamide. Acetone, like DMF, contains oxygen in its molecule. This can negatively affect the carburizing process. Therefore, its presence in the low-pressure process is undesirable for the stability of the carburizing. However, since DMF has a boiling point 100 degrees Celsius higher than acetone, this acetylene solvent will most likely not enter the working chamber, and the process will be more stable and safer. Once we have carburized the parts, the next operation is quenching. This is fully up to the user. The quenching methods are described in detail in the course on classic carburizing. We will just review them. We can harden directly from the carburizing temperature, with pre-cooling to the optimum quenching temperature, with cooling below A1 temperature following by reheating to the optimal quenching temperature, or with cooling below Martensite start and new reheating. Or we can even harden separately on the layer and separately on the core. There are many ways. However, in low-pressure carburizing, the opinion has become established that if we harden in a gas stream, in nitrogen or helium, we harden directly from the carburizing temperature. If we quench into oil, we must pre-cool the load S from the carburizing temperature to the optimum quenching temperature. If we have a single-chamber vacuum furnace with 15 bars of nitrogen, and LPC is only there as an extension of our technological capabilities, we have no choice. Unless there are any major reasons against it, we will quench directly from the carburizing temperature. However, if it is necessary to quench from the optimal quenching temperature, then we must let the furnace cool down spontaneously to the required temperature, heat the load again at this lower temperature, and then quench. It will cost us 2 hours of non-productive time. Other hardening methods, with a decrease below A1 or below MS temperature, are so unfavorable that these processes cannot be carried out responsibly for economic reasons. If we have a 2-chamber quenching furnace, in the case of gas quenching, we quench directly from the carburizing temperature. The load is transferred from the heating cell to the quenching chamber and is cooled by the gas over pressure. In the case of oil quenching, we must pre-cool down the load to the optimal quenching temperature. This can be done in 2 ways. Either we let the carburizing chamber with the load cool down to the required temperature, and as soon as the entire load reaches the required quenching temperature, we transfer it into quenching chamber with the oil and quench it. Or we can transfer the load to the cold chamber, cool down in this chamber by spontaneous cooling or under a fan, and then introduce it back into the carburizing chamber for reheating. But this time to the optimal quenching temperature. This is a similar procedure to that of multipurpose furnaces with one-sided loading. The condition is that the furnace's handling mechanism must work in both directions, that is, there and back. If it is only one way, we must always make pre-cooling in the heating chamber, or we must slowly cool the batch in the quenching chamber, take it out of the furnace and return it back in front of the first chamber. Then heat it again, this time to the optimal quenching temperature, and then quench. The energy consumption will be almost double, and the process time will be 50% longer. A great advantage in choosing the quenching method is provided by multi-chamber systems such as ECM Flex, Jumbo or Nano, or ALD Modultherm. Here we will take advantage of the fact that we have multiple working chambers and each of them can be at a different temperature. We only transfer the load from one chamber to another and then quench it. At the same time, the parts are still inside the vacuum system. In this type of equipment, it is possible to model all methods of quenching after carburizing quite easily and with almost unlimited temperature options for a given operation. This simplified model shows the ECM Flex device with an inlet and outlet module, 2 heating cells, and a quenching chamber with 20 bar of nitrogen or helium over pressure. In one chamber, we do the parts carburizing at 980 Celsius. In the other, we cool down the load to a quenching temperature of 860 C, and then we quench in a gas stream. The advantages and flexibility of this system are quite visible. Recently, so-called hybrid systems have also been developing rapidly, where we can have both quenching in oil and in a gas stream. This significantly increases our flexibility. A much-discussed question is whether it is more advantageous for us to quench in the gas stream or into the oil after carburizing. The answer is not clear. Each case will be different. It all starts and ends with the CCT diagram and the cooling rate needed to achieve 100% Martensite. However, since the total load can behave quite differently, the critical limit between hardenability in oil and in the gas stream must always be verified in advance. It's not that simple. The figure shows a CCT diagram for 100 CR6 bearing steel. In order to quench the parts properly, we must have a cooling rate of at least 40 Celsius per second. The result is in the picture. In terms of hardness, the parts hardened in 20 bar nitrogen were perfect. However, the structure was flawed because there are inadmissible phases of trusted. This is not visible at first glance. The cooling rate was therefore just at the limit of possibilities, but the presence of trusted was the impulse to exclude nitrogen from the considered variants. Each steel has a chemical composition within a certain tolerance band for each alloy. According to the standard, for example ISO 683 Part 3, hardenability zones are defined for each steel. Therefore, in order to have stable results, we must be in the upper range of alloying. Under optimal conditions in this band, the steel will be hardenable in a gas stream, but as soon as the chemical composition corresponds to the lower hardenability range, we will not be able to quench this steel in nitrogen. ALD has published this table, which can help a lot in our decision-making. With Category 1 steels, we have to be very careful if we choose nitrogen. Category 2 steels will always be hardenable in nitrogen, but these are mainly tool steels. In Category 3, there are steels that can be quenched in helium, but not in nitrogen. This diagram shows the cooling rates for nitrogen and helium in single-chamber furnaces and in double-chamber system with cold chamber for quenching. They show that the use of single-chamber systems is very impractical, because with each load, we cool down not only the parts and baskets, but also the entire hot zone. So, we must have at least 2 chambers, one for heating and carburizing, and the other for quenching. The efficiency of cooling in gas stream will increase by an order of magnitude, but we are still not at the level of oil quenching. Switching to helium can help, but this gas must be fully recovered due to its price, so it is an extra investment. And since this investment is roughly equivalent to the price of a good washing machine with modified hydrocarbons, we have to consider carefully what is more advantageous for us. We also have to consider the requirement for strength or hardness in the core. This is related to hardenability and hardenability bands. Small, tiny parts will work out strong, but there will be a problem with large parts. For example, with parts made of 16 manganese, chromium 5 or 20 manganese, chromium 5 steel, we will be successful with hardenability up to a diameter of 20 millimeters. Above this size, the results will be uncertain. We will have a hard carburizing layer, but the core will be soft. So it can be clearly said that if we do not want to take risks, if we want the same process stability as in existing multi-purpose furnaces, we must quench in oil steels that can be hardened in water or oil, in gas are only occasionally hardenable. The steels that can be hardened in air or in a gas stream are always hardenable in oil. So if we are thinking about flexibility and the future, then we need LPC with oil quenching. If we have a stable product and a proven process, we can consider gas quenching. When deciding to purchase a low-pressure carburizing equipment, it is important to look at it from the perspective of energy consumption and impact on the carbon footprint. The LPC technology itself is emission-free, as are other vacuum technologies. For comparison, we can give an example of a load of 1,200 kilograms of goods plus 300 kilograms of fixtures, carburized to CHD, 1.5 millimeters, processed in an ECM Eco 1299 furnace with oil quenching. The model process consists of heating to the carburizing temperature, then the carburizing itself at 960 degrees Celsius, cooling to the quenching temperature of 840 degrees Celsius and quenching in oil. The total electricity consumption is 657 kilowatt-hours and 2.57 cubic meters of acetylene. The process time is 13.8 hours. The emission factor for acetylene is 3.93 kilograms of CO2 per cubic meter of gas. The emission factor for electricity is 0.34 kilograms of CO2 per 1 kilowatt-hour. So we will have 233.48 kilograms of CO2 per process. If we were to carry out the same process in multipurpose furnaces, the situation would be as follows. We have to go down in temperature, because the maximum temperature on Ipsen furnaces is 950 degrees Celsius. We will have an endo-type atmosphere and the addition of propane for carburizing. The total emissions for the same process will be 770.4 kilograms of CO2, almost 3 times more. Therefore, low-pressure carburizing is demonstrably more advantageous in terms of emissions. The advantages of low-pressure carburizing are evident. This figure shows the electricity consumption for the quenching process in the LPC furnace and for the different carburizing depths for the reference load. The economic advantage increases with the required CHD, and we can achieve up to 60% savings. This, of course, will be reflected not only in the economy but also in emissions and lower carbon taxes. The reason is the possibility to work not only with better insulation properties of vacuum furnaces, but also with higher temperatures and higher diffusion rates. As a result, our investment in LPC may be priced lower than the investment in the line with multi-purpose furnaces. An example is in this picture. The lower investment in LPC is due to the fact that we need one less carburizing cell for the same capacity requirements than in the case of the purchase of the classic sealed quench line. This is due to shorter process times. Similarly, the resulting price for processing can be lower for low-pressure carburizing than from multipurpose furnaces. Although the share of depreciation in the price of heat treatment may be higher, it is fully compensated by savings in processing time and energy savings. There can be a whole range of low-pressure carburizing equipment. We can start with single-chamber furnaces, but I consider them unsuitable for this technology. First, we must reheat the carburizing chamber every cycle, and at the same time, the heat capacity of the heating chamber reduces the cooling rate where I need it most. In the case of quenching in gas stream after carburizing, this is a device for testing rather than production. Next in line are 2-chamber or 3-chamber furnaces. Here we already have the same cooling conditions as in multi-purpose furnaces. The quenching chamber is either with oil or adapted for quenching in gas stream. In both cases, we have ideal conditions for hardening parts. The 3rd chamber has various uses. For example, in Seco Warwick, it is used for applying the preneat process, in ALD or TAV as a transfer chamber when handling the charge between the heating and quenching module. A concept can also be accepted where one end chamber is for gas quenching, the middle chamber is for carburizing, and the other end chamber is for oil quenching. The batch is always loaded through the nitrogen quenching chamber, but after quenching it is taken out, depending on which quenching method was applied. However, since multi-purpose furnaces are also used for other types of processing than carburizing, to be able to carry out these processes, we need additional furnace equipment. For example, to be able to carry out normalizing, the oil quenching chamber should be equipped with a cooling fan and the possibility of nitrogen cooling up 1 bar absolute pressure. The same applies to various annealing processes. In these, currently predominantly two-chamber systems, it is also important that the loading of the clean load into the heating chamber and the handling of the load during oil quenching, including its removal from the furnace, are separated. Otherwise, we will permanently pollute the heating chamber with residual quenching oil clogged by this transport mechanism. The heating chamber should have the possibility of placing a convection fan to improve the uniformity of heating, and the possibility of partial pressure. We must realize that unlike multi-purpose furnaces, these heating chambers can reach temperatures up to 1,250 Celsius, and our processing range can be much wider than before. In order for these furnaces to be included in an automatic line, unlike single-chamber furnaces, they should have entrance doors that can slide horizontally or vertically. Then, standard rail loaders, robotic loaders, or even robots themselves can be used for loading and unloading. The last category are multi-chamber furnaces. This solution has been mastered by only two furnace manufacturers, the French ECM and the German ALD. Both companies have a hybrid solution. I mean, they can have both a gas and oil quenching module in the line. The most widely used type of furnace is the flex system from ECM. The modular vacuum tunnel allows you to connect working chambers that can be of different purposes. For carburizing, for heating to high temperatures up to 1,250 degrees Celsius, for brazing, tempering, or nitriding, and nitro-carburizing. Inside the vacuum tunnel, there is a transport system that transports the batch between the individual chambers in a vacuum. Up to 14 of these cells can be installed in this way. However, it depends on the implemented technology, because we still have to keep in mind the time between the batch being removed from the carburizing chamber and being introduced into the quenching module. The input or output chamber has the function not only for loading and unloading the batch, but also for its forced cooling. For example, in the case of normalizing, after soft annealing, after isothermal annealing, etc. A similar logic is used in the jumbo-type equipment from ECM or multitherm from ALD. In this case, loading and transfer of the batch is carried out via a transport system without a vacuum tunnel. In the case of ECM, the batch is fed after heating into a special chamber for quenching in a gas stream or in oil. The specialty of ALD is that this transport module is also a module for quenching up to 20 bar of nitrogen or helium. All these systems are fully expandable. We can therefore start with a minimum number of heating cells and gradually add more according to the increasing capacity needs. The new product from ECM is the Nano system. This device completely changes the view of the heat treatment line. It works with small batches up to 100 kilograms, but their movement between the chambers is not horizontal, but vertical. There can be 6 heating chambers with dimensions of 500 by 600 by 250, or 12 with dimensions of 500 by 600 by 150. The device can have both oil quenching and 20 bar quenching in a gas stream. In this case, however, either and/or is valid. The basis is a vertical transport chamber with 4 free positions for installing the device. 2 positions are occupied by columns with heating chambers. The third position is a quenching module. If the Nano is with oil quenching, the load cannot be placed through this module due to possible contamination of the heating cell with oil. It can only be taken out of the furnace after quenching. If there is quenching in gas stream up to 20 bar, the load can be loaded and unloaded through this quenching module. However, it must be considered that in a configuration with 12 chambers, the cycle time between hardenings will be only a few minutes, and it is a question of whether we are able to plan the loading into the furnace in such a way that there are no downtimes. The fourth position can be occupied, for example, by an input and output module, or it is simply blinded and used for maintenance of the elevator in the transport chamber. There are many variants. The advantage of this system is the high flexibility of heat treatment. Each chamber can be at a different temperature, high reproducibility, and full automation. The entire line is fully automated and allows operation in 24/7 mode. Peripherals such as tempering furnaces, washing machines, freezing are then connected to this device. In combination with robotic load preparation, robotic unloading, and disassembly, we can create a fully autonomous, unattended workplace for heat treatment. It is not without reason that the system was given the marketing name All-in-One. Everything that was previously stated applies to carburizing in this system, but because we have 6 carburizing chambers, for example, for CHD 0.6 millimeters, the quenching frequency will be up to 11 minutes. This means that in this device, we can carburize up to 545 kilograms of charge, including grates in 1 hour. And this is more than in a conventional multi-purpose furnace with the load of up to 1,500 kilograms. Finally, I would like to mention the cost of equipment validation. Every device must undergo regular inspections to make sure that the achieved vacuum, working pressures, or flow rates correspond to reality, and the same applies to temperatures. We must be sure that if we set the required temperature of 960 degrees Celsius on the furnace, the actual temperature will be exactly that. How this is done is described in ISO 20431, CQI 9, or AMS 2750. In multi-purpose furnaces, we must perform periodic or continuous control of the carbon potential, and these methods must be supervised by a different method. A common combination is 2 parallel oxygen probes, or an oxygen probe and dew point measurement, or an oxygen probe and an infrared analyzer. Measurement of the carbon potential using the foil method is also possible. In any case, the cost of oxygen probes and their calibration is excluded with low-pressure carburizing. The maintenance of equipment for LPC is therefore significantly more economical than that of conventional multi-purpose furnaces. Instead, we are only obliged to calibrate mass flow meters to acetylene once a year and vacuum gauges in the same period. The total cost of validation of a low-pressure carburizing furnace will therefore be 40% lower than the cost of validation of conventional multi-purpose furnaces. The last note on low-pressure carburizing is its operational safety. Using an endo-atmosphere for carburizing has its risks. When at temperatures below 750 Celsius, the endo-atmosphere becomes explosive. This is not unusual when we load a batch into a preheated furnace. The temperature in the furnace after loading the batch often drops below this limit, and the furnace must be gassed with neutral nitrogen. The second risk is fire. Even if the furnace is tight, and all combustion processes take place inside without the presence of oxygen, in the case of loading and unloading, the door must be opened and the tightness of the furnace must be ensured by flame curtains. This can be critical, especially when quenching small parts in oil, where there is an unfavorable ratio between the surface area of the batch and the amount of oil on the parts. The fact that it cannot happen is just a belief. The reality is different, and every heat treatment plants with multi-purpose furnaces has at least one, often more, of these unpleasant experiences. Another safety issue is the purity and possible contamination of the oil with water. Due to exothermic reactions, water in the oil will be a critical parameter and must not exceed 0.1%. The result can also be interpreted according to the following video, which shows the reaction of hot slag in contact with a snowfield. Nothing like this can happen with low-pressure carburizing. We work with vacuum and at low pressure, where even the proportion of acetylene in the exhaust from vacuum pumps cannot be a source of ignition. Investing in LPC is therefore much less risky and can also be reflected in the costs of operating insurance. The low-pressure carburizing course is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels, so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to ASCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a permanent license for €500 per course. The compressed zip file will be 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0 on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, at home, and you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.